Okay, here we are, Reverb 2, our second note set in Unit 4, where we're talking about reverb, or RVB as I use for the abbreviation. I'm going to base these discussions largely on these sections of this book by Boaz Parat. It gives a pretty nice coverage of these things. There's also a little bit in Proaicus and Monolacus, but I think Parat covers that as well. And then there's also a little bit in the DASP book, but this is the main thing. So what are we talking about here? We've alluded to convolution reverb. We've said in concept, in principle, it's super easy to think about, but it's very challenging to come up with a way to computationally implement it so that we can do real-time computation with reasonable amounts of processing power. So this unit or this note set is just some preliminary stuff leading to the real algorithm that we'll use. And it's talking about two different things that are common in just standard DSP classes. So if you've had a standard DSP class, you may have had this stuff. It's the overlap add or overlap save FFT-based method for implementing FIR filters. So that's what we're talking about here. So just a reminder that we're talking about the complexity issues with convolution reverb, but it's not just about reducing the number of operations that we have to do per second, or even just the total number of operations that we have to do for a particular computing and output point. The point is also that in addition to reducing the number of computations, we also have to reduce what's called the latency. We have to make sure that we have a negligible latency in computing the output. That just means that if it for some reason, and we'll see the reason that we're worried about here, but if for some reason, no matter how fast a computer we have, we can't compute the output until later, that's a problem. And we can't really do this in a real-time fashion. So we'll take a look at that. So latency is just a general term that just means a delay due to the lack of availability or timely availability of output data. And this is different from the delay that we talked about that's inherent in a filter that's group and phase delay. That's not what we're talking about here. The group and phase delay is a delay in the filter or in the input to output due to phase shifts. But that's not what this is. This is we have a bunch of data that's coming in, and we can't compute the output now without some delay. That would be a latency. So what we're going to do in this note set will not address this latency issue, but we will see that we can reduce the number of operations that we need to do. But it does not solve this latency real-time issue. In fact, it makes things worse, as we'll see. But it ends up being a building block to another clever little thing that will allow us to beat both of these issues, the number of operations and the latency. So let's just motivate this idea, what we're going to do. I said this is an FFT-based way of implementing an FIR filter. So yeah, we're thinking about implementing the filter over in the frequency domain. Listen, all the standard ways of implementing a filter, there's just two that you really should know about. Well, three actually that you know about now. Convolution, recursive solution of a difference equation, or the recursive solution of the state space model. One of those three. Those are all time domain implementations. But we do have these two different views of filtering. We have the time domain view, which is convolution, and we have the frequency domain, which is multiplication of Fourier transforms. And so if you've not watched previous note sets, this notation here might be a little bit odd. I'm following the notation from Peratt's book. So he uses theta as the discrete time frequency variable. Most other books use capital omega. Proachus and Montelachus, much to my chagrin, or not chagrin, but much to my dismay, use a little omega. I don't like to do that. I generally use capital omega. So remember, this is in radians per sample. Goes from minus pi to pi. Well, that's what theta is going to be here. Same thing, just a different symbol. Peratt likes to use the theta. And there's a logical reason for that. I'm just not going to bother getting into that right now. He also uses these superscripts so that we know that it's a function of theta, but we know that it is a DTFT. That's what that non-italic lowercase superscript f tells us based upon his scheme. So we're talking about DTFTs. This is the DTFT of the signal, and this is the DTFT of the impulse response. That's the frequency response. So this DTFT frequency domain view is kind of the key to understanding how to analyze and design filters to see what they do. We talk about pass band and stop band by looking at the magnitude of the frequency response. We talk about the linearity of the phase and the group delay and the phase delay and things like that. That's all for analysis, but when it comes down to implementing, we either do convolution, we do recursion, one or the other. Okay, so that's the deal. But now, could we somehow come up with a new way to implement based upon this DTFT view? So could we compute the DTFT of the input signal and the DTFT of the filter, that's the frequency response, multiply the two and take the inverse? This is a question I'm asking. Can we do that? No, not inside a computer. And the reason is that the DTFT exists at an infinitely many frequency values, right? It's at every point between minus pi and pi. So technically we cannot do that. Now you might say, well, the DFT, at least in the case where these two things are finite duration, then the DFT would give us exact points on those two things. So that might work. We're talking about implementing an FIR, and obviously in audio applications, the signal duration is finite, so we could compute the DFT of that. So, and we can use zero padding. We can get that as fine as we want, but how do we mechanize this? How do we make sure that this actually works? And there are some gotchas in this, and that's one of the big things about working with a DFT. It does some weird things compared to what happens with the DTFT. So if the input signal is finite length, the DFT computes samples of the DTFT, and likewise for the filter impulse response. So can we do this? Take our signal, n length, compute an endpoint DFT, take our filter. If it's not n length, we would zero pad it out to n length, but we don't know. Do an endpoint DFT. Now those two things, those two FFTs have to be the same length so that we can get two things that multiply point by point. Then we do an endpoint inverse DFT, and the question is, do we get the convolution that we want? That's a question. I'm asking that. And the answer is, well, not necessarily. And that's the gotcha. There's a gotcha when you are going from things you know that the DTFT does to things that you wonder if the DFT does the same way. And be careful. There are some gotchas, and this is one of those. If we do compute those two DFTs and we take the inverse DFT of that, this is just a theorem that's proved in Peratt, it's proved in a couple of, most every other DSP book. We don't get the convolution between them. We get something that's like convolution, but it's called circular convolution or cyclic convolution. It's different. That's the gotcha. So we don't want cyclic convolution. We want ordinary convolutions. So we have to worry about this. So I said not necessarily. So that implies that it might work sometimes, but not other times. So now a question, I'm asking it again. When does it work? And that's the key to understanding this idea that we're talking about in this node set. We have to trick the DFT into the circular convolution that it does ends up being identical to the linear convolution that we want. So the more you know about the theory of DFTs and how they link to the theory of DTFTs, the better armed you are to understand these things. Now, I'm not going to go through all the theory here because this is not a theory course. But I'm going to ask another question. So it's really just recasting this question. When does cyclic convolution equal linear convolution? And we could prove this, but it would be not terribly enlightening. I'm going to simply illustrate with an example and then tell you the general result based upon that. So here's an example. Suppose we have two very short things that we want to convolve. So some signal x of n and some filter h of n. And usually signals are longer than filters, so I've made that the case here. But again, this is a very short problem that we would never encounter something this short in an audio application. But the length of our signal is 9 samples, and the length of our impulse response of our filter is 5 samples long, and zeros elsewhere. So let's look at linear convolution. So you may have learned how to do this in a signals and systems class. We take this, well, let me back up. We take this and we simply rewrite it in a dummy variable m. Could be anything. Could be k, could be l, could be r. I chose m. Then we're going to take this and also write it as a dummy variable m. So really all I have to do is just change those two symbols. That's it. Now the next thing I'm going to do is flip this around the m equal to 0 point. So I'm going to anchor it there and flip it. And so now I get this. And so now this I label h of negative m. So I flipped. And if you remember, convolution involves this flip once and then a whole bunch of shifts. So for each output sample, I'm going to have to shift this by some amount. So if I want to know the output of the convolution of these two things at n equal to 0, I flip, but no shift. And so that would be the case for n equal to 0. In general, we'd have an n minus m in there, but for n equal to 0, we just have the flipped version. So we flip and shift of 0 here. We multiply. What do we multiply? Point by point by point by point by point. So in this case, the only non-zero product is right there. And then we add up all the products. So we're going to add up a bunch of zeros, we're going to add up that product, and we're going to add up a bunch of zeros. So it ends up just being that product. That's it. That's what comes out at n equal to 0. Now, you'll notice that, let me go back here. You'll notice that if I shift to the left, that would be for n values less than 0. In that case, let's just shift it back by 1. This will be lined with that. That'll be lined with that. This will be lined with that. We see that all of our products are equal to 0. In fact, for all negative n, all of the products for this example will be 0. So that means our output will be 0 all the way up until this first non-zero value at n equal to 0. Then we keep shifting it to the right by 1. So when we shift it to the right, now those two are lined up and those two are lined up and everything else is 0. So we add up those two products and spit it out, and that's our output at n equal to 1, and so on and so on and so on until we get to this position. Now we are at n equal to 12, and I'm just showing you that it's n1 plus n2 minus 2. So that would be the general scenario for N1 and N2 being the lengths of the two things that we're convolving. That is the last time that will have any non-zero product. So we'll get an output at n equal to 12, but then if we go one more, n equal to 13, those two will be lined up, those two will be lined up. Every product will be 0, and we'll get 0 out at n equal to 13, and likewise for 14 and 15 and so on. So what we've seen is that the values where we have potential non-zero outputs, yeah, some of those in the middle could be 0 if the products add up to 0. They wouldn't in this case. But we're going to have output values of non-zero potential for those output indices. And there's going to be 13 of them. So 13 corresponds to N1 plus N2 minus 1. So our last output is at N1, N2 minus 2, and that is the total number of non-zero, potentially non-zero output samples that we get. And so we now have a way of saying that's the length of our result. So that's interesting. So keep that in mind, the idea of shifting this through, what those shifts look like, and how many of them we had. Now I'm going to show you what cyclic convolution looks like. Now, in a DSP course, we would prove why we get cyclic convolution, and we would look at this. Sometimes books show it with the signal samples populated around circles. I find the circles to be difficult to view. I like to look at it this way. This is completely equivalent to the circular view that most DSP books will show you. So here's how we do circular convolution. Remember, we don't want this. We're just trying to understand what I would get if I took this shorter signal and zero padded it out to the length of the longer one. And now I could do a DFT of that and a DFT of that, do the product of them, do the inverse DFT, and we want to see what we get. And our theory that I stated on a previous slide, we didn't prove it, but I'm just stating it. The theory says the result of that is circular or cyclic convolution. And this is what you would get. So the first step is zero pad the shorter signal to the length of the longer one. So here we're assuming that we do a DFT the size of the larger one. We'll address what happens if we were to zero pad the longer one also out to a longer addition. We'll get there. So we zero pad the shorter signal to the length of the longer one. So that's what we have here. And then here's the key to doing the circular part. We periodize them. So that's that's the view I like to take. Most books will say, now take both of these and put them around two circles, and then we'll look at how those samples interact when we do convolution, where instead of a shift, it's a rotation of those circles. But I'm going to do it this way because this makes it a little clearer how it's linked to linear convolution. So I periodize each, where the period is now the length that we've zero padded the shorter one out to the length of the longer one. So here's the next period, and here's the previous period, and so on. And I've color coded these just to make it easy. So that's the first two steps for circular convolution. I'm just defining something new, telling you how it works. Then to find our first output sample, we flip the periodized version around this point. So we could flip either one, but I'm going to flip the one that was originally shorter. It's just a little easier to see it that way. I'm going to flip it right around this point, and I'm going to flip the whole periodized thing. So look, the red one comes over here, the black one goes all the way over there, the green one goes all the way over there, and the blue one goes right here. But now it went this direction, now it's going that direction, right? Ramp up, constant. Ramp up, constant. Okay, so that's the flipping. It's anchored there. Now, the next thing in the definition of how cyclic convolution works is to find the output at n equal to 0. We then take this flipped version, and we do all the products, but we only need to sum over one cycle. So we really only need to do the products over one cycle. Don't need that. Don't need that stuff. Okay? But now notice something happens. Here is the same product that we had in the linear convolution. Because remember, these were all zeros here. These were all zeros here. This was all zero. This was all zero. So that was the only product, non-zero product that we have. And we have it, but we also have all of these products. Oops, not this last one, just these here. We have those, and they were not there. So the answer we get for n equal to 0 for the circular convolution is not the output that we would get for n equal to 0 with a linear convolution, because 4 additional things are being added in. Now, the next thing we need to do is shift. And here, this is the thing that I like about the periodized version. We just shift along the axis just like before, but we have to shift the whole periodized thing. So this thing's going to move to the right by 1. All of these will move to the right by 1. These will all move to the right by 1. And so now what do I have? Now I'm going to have those two aligned, those two aligned. We'll have some zeros here, but now this is going to align with that. This is going to align with that. This is going to align with that. Whoops, what am I doing here? Yeah, that's right. That's fine. Yeah, and that one got moved out. I was stumbling there for a minute. That one got moved over into this position, and so it doesn't have anything to do. But notice that there are still 3 products that we would not have in linear convolution. So what we're seeing here is that the first 4 output samples for this example will be wrong. Now let's continue on. Eventually we're going to keep shifting, and we'll get out to a shift by 8, and we'll be in this position. So we've done no shift, shift by 1, 2, 3, 4, 5, 6, 7. Some of those were right, or some of those were wrong. And as you'll see, some of those actually turned out to be all the same as linear convolution. Exactly like this position is for n equal to 8. Look at this. These all end up not forming or forming 0 products, and these form 5 products that are exactly the same as in linear convolution. So the n equal to 8 term is correct. And in fact, n equal to 7, and I think maybe even n equal to 6, maybe a few others. So there's going to be some that are wrong and some that are right. And that's weird. But now what happens if we try to go a little bit farther? Remember, we had n equal to 12 was our last output when we did linear convolution. What happens if we go to 9? If we go to 9, now this thing's going to move in here, that's going to move to here, and these are all going to move over 1. That's exactly the same case we had for n equal to 0. So the output has the same periodicity, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. So at n equal to 8, we will have already computed 9 values. So the output has the same period as the input. And so it starts to repeat. So we would say that the length of the output cyclic convolution is the max of the largest, or the max of the 2 lengths. So the largest length of the 2 signals that you're circularly convolving. And so that's definitely different. So we're seeing not only do we get wrong values, we get some right values, but we don't get the right number of values even. So there's a lot of things going wrong. So this seems to say that our hope of doing this DFT-based FIR filtering, or in other words, computing convolution using FFT or DFT, maybe won't work. But we have to see if we can fix this, and that's the thing. So lots of stuff in engineering and signal processing in particular you hit a roadblock, and then you have to be clever and ask, can I find a workaround for this? And here we can. So these are the issues that tells us that there is a problem, but let's see what we can do. And here's my claim, and I'm going to tell you to do this and go back to this example and check that it works. Best way for you to see it, rather than me spending time walking you through it, is for you to actually do it and verify for yourself. But if we choose n1 plus n2 minus 1, remember that's the actual length of the linear convolution that we expect. So if we pick a number k that's at least that big, it's going to be an integer, and then we zero pad each signal out to that length. So let's go back to where we did our zero padding for the circular convolution. Here we zero padded the shorter signal to the length of the longer one. What we're really going to do is now stuff in some more zeros there and more zeros there so that we have 13 values in a cycle. Then we'll be able to get 13 output values before things start to repeat. And my claim is that all of those values will be exactly the same as what you have for linear convolution. So your job is to pause the video and go and check that out and make sure you understand why. So here is a simple FFT-based implementation of an FIR filter. So notice I'm stressing simple. We'll see that this solves some problems and is applicable in some scenarios, but creates other problems for our scenario. So here I am zero padding both the signal and the filter out to some length k that satisfies that. And that will ensure that when I do this product and take the inverse FFT of that, the thing that I get out over here is going to be the actual convolution. Now, if I went k exactly equal to that, I'd have all the correct values that I want and nothing more. But if I pick k strictly greater than, and there may be times when I want to do that, then there will be some extra zeros at the end. How many extra zeros? However much bigger k is than that will tell you how many extra zeros that you'll have there. Now, I just cycled through some boxes here that I should probably talk about. For our computational complexity viewpoint, we need to remember that we're implementing a filter. So this DFT here can be pre-computed. I say usually, but it's almost always pre-computed. So we would just pre-compute that. We don't have to count that against our complexity. And then this product here would be this product of the DFTs of X and the DFT values of H, and then we do the inverse FFT to get back. And so why do we do this? Well, in many cases, and we'll figure out how to determine when that is true and when that isn't true, but in many cases, even though this seems much more complicated than just direct convolution of these two things, it actually requires fewer computations because of the FFT's efficiency. That's the key to this. If we didn't have the FFT and we just had to compute the DFT directly, this would not save us any computations. In fact, it would be worse, I think. Never really gone through the computations, but my hunch is that it would be more computations because it looks more complicated. But the FFT is such a clever little algorithm that it actually ends up saving computations. But why did I stress that this is a simple FFT-based method? Well, there's some problems with it. So what if our signal length is much, much longer than our filter length? And that's usually the case, right? We might have a filter of maybe just a couple hundred taps, a couple hundred samples, but our signal might be an audio signal that could be several minutes long. Remember, 44,000-ish samples per second, so that's a lot of samples. So what does that have? Well, remember we have to do FFT that's bigger than the longest one. So if this is really long, that means we're going to have a really big FFT. And as good as the FFT algorithm is, really big FFTs are going to be computationally burdensome. But that's not the worst of it. The worst of it is that you can't get any output samples until you've collected the entire signal. That's the biggest problem with this simple FFT-based method. You have to bring the whole signal in. So if you're in a real-time application, you get the first sample, the second sample, you have to wait. So if you want to filter a song that's 4 minutes long, you can't start doing anything until the song is over, and then you can compute your FFT and start putting the signal out. So very long latency. That's where this latency comes from in this algorithm. Just waiting to get samples before we can start computing the FFT. So there we have a filter 4 minutes of audio signal sampled at 44.1 kilohertz. So the size of N1 is 10 to the 7th. So we're going to have a huge FFT. FFT is on the order of maybe 8192 samples, 16384 samples, 32768, maybe one more power 2 above that, 65. I can't remember the power 2 there, 65,000-ish. Those are big, but not unreasonable. But 10 to the 7th, that's a ridiculous FFT size. We would never want to do that. And then what if we don't know N1 in advance? So remember, we have to zero pad H out to something a little bit bigger than N1. And we'd like to be able to pre-compute the FFT of the impulse response. But if we don't know how long the song's going to last when we start, say we're implementing a filter that we're going to play live through, who knows how long I'm going to play that song for. So we don't know N1. So we can't really pre-compute the DFT of the filter. So that's bad. That just creates one more large FFT that I have to do after I collect the signal. So this is not good. These are some serious limitations to this, but we're just setting the stage. We've got an idea in our mind now. Well, we can do convolution using DFTs, but there's some problems. Maybe we can find some ways around those problems. So let's do that. Here's a better FFT-based way to implement an FIR filter. So there's actually two methods. They're very similar. I'm going to first introduce overlap add in a lot of detail. Then we'll talk about overlap save in a little less detail. It'll turn out that we'll use overlap save to do convolution reverb, but we could use overlap add as well. It's just that Gardner's paper used overlap save. There might be a small advantage to overlap save. I'm not really sure off the top of my head, but that's what we'll end up using here. But I want to cover both. I had some existing notes for overlap add, and those are nice, so I'm going to do that first and then just piggyback on that to show you how overlap save differs. But the basic idea is they're both exploiting the fact that we're implementing a linear filter. So we can break things down into blocks and we can process each block. And the easiest way to see this, and this is really the basis of the overlap add, we break this down into non-overlapping blocks. We'll see that on the next slide. But if we look at x of n as a sum of a bunch of finite blocks, now we can say, well, if I put in x to be convolved with h, and this is just Peratt's little idea of notation. We convolve the two and we're looking at the nth value of the output. A lot of people write it as x of n convolved with h of n, and there are some mathematical issues with that notation, but let's not worry about that. But this is a nice notation. So by linearity, we just pass the convolution through this sum. So now we're convolving H with each individual little block. Aha! Now we've eliminated this issue of having a really long signal. We can set the size of the blocks ahead of time. So no matter how long the signal is, we know the size of the blocks. So we can set things up in advance. We can compute, we can zero pad our impulse response and compute its DFT and just do this block by block. Each time we get a signal block in, we can do this convolution. Now, that doesn't eliminate the latency, it just significantly reduces the latency. Now, we'll see in the next set of notes something even more clever that will allow us to completely eliminate the latency. And that's remarkable. That's what we want. So we compute a block by block convolution, and then we add those results. So that's the overlap add, OLA. So, and how do we do those individual block convolutions? Oh, we just use the simple method that we just learned about. See how this all builds. One thing we learn, and then we say, oh, that's a problem, but now we're going to do a new thing, but it's based upon the old thing. So the main difference between the overlap add and the overlap save is how these blocks are handled. So for overlap add, we're going to say, let the impulse response have some length n sub h. Yeah, I was using n1 and n2 in previous slides, but we've graduated now to this, h, n sub h. And then we're going to let the signal x of n have an undetermined length. We're streaming it in. It could go on for who knows how long. Just keep going on. But what we can do is choose the length. We get to choose the length of the blocks, and we'll call that n sub b, b for block. So that x sub I of n is a non-overlapped block, and the blocks are contiguous, so we're not skipping any samples, and we choose nb to be bigger than nh. Then we're going to zero pad each of those. We'll zero pad nh out to nb plus nh minus 1 or more, and we'll zero pad each block out to that value as well. But I'm getting ahead of myself. Here's how we define those blocks. It's just classic math. I have a little block counter here, and so I'm just going from the start of a block to the end of a block. And this little block, I'm assuming outside of it is 0 everywhere else. That's how I can say just add these things together to give me the x. So here's a little picture. I'm not showing the zeros otherwise, but if I took this block here and imagined it as zeros out here, and then took this block here and imagined it had zeros on each side, we can easily see that adding those things together creates the original signal. So that's the idea. Now, this is an artificially small block size. We'll really use block sizes that are bigger than this. So let's charge on. So here's our input signal, and I'm showing 3 successive blocks. And now I'm going to convolve each one with the filter of some length n sub h. Now we know that the length of that convolution is, if we've done this right, regardless of how we compute this convolution, whether we do the simple FFT base where we zero pad each, do the DFT computation, form the product, do the inverse DFT, and then get back our correct linear convolution result, or we just linearly convolve them. At this point, it doesn't matter. The point is we just want to see how this all fits together. So if I take this and convolve it with some filter, the result is going to get bigger, right? We said the length of the output is, well, back a few slides, it was n1 plus n2 minus 1. So here's the size of the input block, and then we have a few extra. So we can actually figure out, for this example, how long h really was, if you want to do that. Then we take the next block and we find its convolution. Now, notice that the output block always starts where the input block did, assuming the assumption is always that H starts with its first non-zero value at n equal to 0. That's the common thing. If it weren't, we would just redefine our filter so that it did start at n equal to 0. So there's no point in having a delay in a filter in this kind of application. So that means the output starts where the input, so the output block starts where the corresponding input block started. But the output is longer, so longer than the block, so it overlaps a little bit into the region of the next block. So the next one now gets convolved. Its output starts here, ends all the way over here. Notice how those overlap. And what do we have to do? Right? Remember, the input was the sum of the blocks, so the output was the sum of the convolutions from the blocks. So these are all the things that end up overlapped just by putting them in the proper places. And then when we add them up, the parts that overlap are the parts that are going to add. So if we've computed the output from this block, now it just sits there, and we can't really do anything at this point until we get this stuff. Then we add those things together, and that will create this. Now, I didn't show this thing coming down here because there's going to be something that will overlap from the previous block. So I don't really know what's going to go here, but that's the idea. So, and that's what I'm just talking about. Output block has length that's bigger than NB, but the beginnings of the output blocks are separated by NB. That just means the output blocks all start at the same place that their corresponding input blocks started. So they end up overlapped, and you have to add them up. So that's why it's called the overlap overlap add. I'm getting ahead of myself. Overlap save is the second method that we'll talk about. So now we understand what we have to do, and we can lay out the algorithmic steps here. So we've got a filter. It's got a length NH, and we know what that is because we have the filter in hand. That's the filter we're trying to implement. Now our job is to choose a block size. We'll talk more about how we do that later, but we choose a block size and we choose an NFFT size. So there's the thing that we have to zero pad out to make us get linear convolution. So our FFT size has to be at least that big. So we would zero pad out to that. So we would zero pad our signal block out to at least this, and we would zero pad our impulse response out to at least this. But remember, it can be bigger, and there's an advantage to zero padding it out to be the next biggest power of 2. So what we usually do is compute what that is and then bump it up to the next biggest power of 2, and that would be our FFT size. That's because FFT algorithms, as we saw back in Unit 1, FFT algorithms generally most of them need the FFT size to be a power of 2. There are some special ones that are more general than that, but we'll just stick with this for now. So in general, since we can pick NB, we pick NB to give us some power of 2. Now, that still gives us some flexibility as to what NB can be. So remember, NB needs to be bigger than NH, and also we then pick it to give a power of 2 here. And this actually gives us the minimal complexity. And I say see below, but I don't think I ever actually really addressed that. I might address it in my more general notes in my DSP class. So we've chosen, this is all preliminary design stuff that we've done. We've got those all selected. So now we're going to come in and zero pad our H of n and pre-compute that. We pre-compute that. We just do that once. So I'm pointing out here because later when we do the overlap save, things will be different. But for overlap add, we're going to zero pad the H of n and the block. So that's what we needed to ensure that circular convolution gave us linear convolution. So that's what we're going to do. Now we run this. We're going to process each block. So for each I value, for each block, we're going to compute the Zi of n using our simple frequency domain based method. So that means we're going to zero pad our current block out to an FFT. We're going to compute an NFT point FFT of it. We're going to multiply that by the FFT pre-computed of h of n, take that product and compute its inverse FFT, and that'll give us Zi of n, put it in the right position, and if it overlaps with some previous output samples, add those together and put them into the output buffer. Otherwise, just let it sit there until it interacts with the next block's output samples. So overlap with the previously computed output blocks and add it to the output buffer in the positions where it is possible to do that. So that's it. We just loop through here until we've completed all of our signal samples. So we can handle an arbitrary length signal, exactly what we want to do. So let's look at the complexity. I told you that this is going to reduce the number of computations in most cases. Let's take a look and see what is the deciding factor for whether it does or doesn't help. So we need to assess the complexity of this. And I'm going to do a little trick in here just because it's a common trick, but it would still end up better off even without this little trick. I'll comment on that when we get there. So we pre-compute the filter's DFT, so we're not going to count that. We're going to measure our complexity with the number of multiplies we have to do every time we get a new input sample. Now, remember, we're not really computing every time we get a new input sample. We have to wait until we get a block. Then we do it. But then we can count how many operations we do and divide it by how many input samples we were working with. So we get a number that's effectively the number of multiplies per input sample. So we need a measure for how many multiplies, and we're only going to count multiplies. We could count adds as well. But we need a good rule for saying an NFT length FFT costs this many multiplies. So this is a good rule. Comes right out of the Peratt book. There are slightly more accurate assessments, but this one's good enough for our purposes here. We're going to assume, as the case is for audio, that our inputs are real valued samples. There are applications like radar and communications and things like that where our input samples might end up being complex valued for various reasons. But for audio, they're going to be real valued. And so there is a trick. We will see this trick later. But you can do 2 real signal FFTs for the price of 1 complex FFT. If you want to read about that in Peratt, I tell you where to go and read about it. But we'll see that result later as well. So now let's just account for things. So for each pair of input blocks, because we can do 2 blocks with 1 FFT, we're going to put our 2 blocks into this thing and compute 1 FFT on those. It's just a trick. And so we'll use this accounting. So we have that many real multiplies to process 2 input blocks. Then we have to multiply the FFTs. So there'll be 4 NFFT real multiplies. And then we have to do an inverse FFT, which is going to cost us the same as that. So again, I'm getting loose with some of these numbers. It's not important that you know where they come from, but just that this seems reasonable. And then we add all that up. So if we add all this up, we get this total number of real multiplies. Okay. And I've just rewritten that writing in assuming that NFFT was exactly equal to that number. So we picked NB to make sure that that was actually equal to NFFT. And it's a power of 2, although that's not important here. So the number of input samples, we took a pair of input blocks, so each block is NB, so we've got 2 NB input samples. So this many computations per that many input samples. So we just divide those. And so there is our count. So this 4 gets divided by this 2 and gives us this 2 out in front. And I've just done a little bit of other algebra here. That's all. Okay, so that's the number of multiplies per input sample using this overlap add, using this little trick. Now, if we don't do that little trick, it's not going to change a lot from this. It'll change a little bit, but that's not the trick that's giving us the real gain. The real gain is that we're using the FFT. So you could go through and redo this, assuming that you were computing your FFTs just on a single block at a time. Okay, now we need to compare this to doing direct convolution. Well, that's just implementing a regular FIR filter. So every output is just going to be, you have to multiply NH signal samples times NH filter coefficients. So you're going to do NH multiplies, and you do NH minus 1 adds, but we're only counting multiplies here. So number of multiplies per input sample. Every time you get a new input sample, you have to do NH multiplies. So that's it, right there. So now I'm comparing these. Here's my NH multiplies on this side, and here's the thing that I had on the previous slide. That's the number of multiplies per input sample for the OLA. And this is just an equation that comes out of Peratt, but we just went through and saw where it comes from. Now what I'm going to do is, remember I said we had to have a guide for how to choose NB? Well, what we want to do is choose NB to minimize this left side for a given NH. So how are we going to assess that? Well, it's nice to look at that graphically. So here's what I've done. I am looking at the left-hand side of that equation divided by the right-hand side of that equation. So let's go back and look at that. So let's say we divide both sides by NH. Well, over here, that's going to make this be equal to 1. So things are going to be more efficient when for OLA when this ratio is less than 1. So let's just plot this ratio, but it depends on 2 things, NH and NB. Well, let's plot it as a contour plot. So I've got NH values down here, and I've got NB values over here, and I'm imagining plotting the value of this ratio as a surface over this plane, but I'm really just showing it as contours. So think of this as a topographical map on that you're looking at for hiking, right? And so I've labeled the contours here. This contour here is the special one. That's the one that has value of 1. Notice that moving in this direction takes me to smaller contours, and moving in these directions take me to a larger contour. So that means everywhere up here, OLA is better than direct. So that's a lot of scenario. And so that's how we analyze this. We look at this plot and we say, for a given filter length, where is it going to be most efficient? So let's just say we start here. I don't know what that is, like 124 or something like that. So let's say that I have a 124 point FIR filter to implement. So I draw a vertical line at that value of NH. Those are all my possible operating points. As I change my NB, I'll be at different positions on that vertical line. So if I picked, let me make that, there it is. There's the vertical line. Let me just make it here. Suppose I chose NB equal to 100. So now I draw across, and where I hit that, well, so now that's going to be between 0.3 and 0.4. So I'm operating at maybe 35% of the direct time domain. But look, I could get better if I bumped that up to 1,000. Okay, well, we want this to be, that's the block size, not the FFT size. So we would need to pick a number near 1,000 such that when we add 124-ish to it, we get a nice power of 2. Where is that going to take us? Somewhere right around there. Look, we can find the tangent points. If we look at every one of these vertical lines, find where its tangent point is. And I've put a dot. So all these dots here are optimal operating points. And then I just imagined drawing a line, drawing a curve through these contours so that the curve cuts through the contours at the vertical tangent. That's my optimal operating curve. Pick a block size that lies on that curve. So if I'm going to be 80, I go up to that curve. That tells me what my block size is. Now I might have to wiggle it around just a little bit so that NB plus NH minus 1 is a power of 2. But look, this is pretty insensitive. I can move around a lot and I stay pretty much on the 0.3 curve. So I've got some flexibility there. It's not like it makes it really bad. So that's how this works. And we see here that, at least according to our analysis, things would change a little bit if we come back here and we say, let's say that we used a different accounting for our FFT, maybe a little more accurate. Our result's going to change a little bit. If we didn't do this pairing, our result's going to change a little bit. Refining this will make it go down, and changing this will make that breakpoint go up. But nonetheless, this is reasonable. It's in the ballpark. So what are we seeing here? We're seeing that for filters that are, according to our analysis, filters longer than 19 filter points are going to be more efficient using overlap add. That's remarkable. That means almost every filter that you're going to design will be more efficiently implemented from a computational complexity point of view, not latency. Because remember, we can't get any output. Our very first output can't happen until we've collected one entire first block. So if our block size is really big, that might not be good. We might have to wait too long for the output to come out. But in many applications, that's not an issue. That much latency might be perfectly okay. So you have to assess it for your application. For audio, though, that's not good. And remember, we're talking about implementing room impulse responses, not 200. We're talking about maybe 40,000, 100,000, 200,000. So as we go way out here, this curve does level off some, but it does keep going up. We're going to be getting to block sizes that are pretty big. That's a quarter of a second right there. That's a long time to wait to get output, right? If you're playing guitar and you want to hear the output, you want to hear the note you just played, you don't want to wait a quarter second for it. In fact, even just a few tens of milliseconds is going to screw up a musician playing. So we don't want that. So you can already see we're heading to a point where even this is not acceptable. That's why we have the next note set. Okay, so that's overlap add. let's talk about overlap save, because in the next note set, that's what we're really going to use. But it works very similarly to overlap add. We just have to do things a little differently. So I'm not going to go into as much detail as to how it works and why it works, but it works. So overlap add, we set things up so that everything we get out of the inverse DFT is a valid result. And we keep everything, and it overlaps with the next block. In overlap save, we're going to set things up so that the things we get out of the inverse FFT, only some of them are good and some of them are bad. So we're going to have to learn how to take the right stuff out. And what that means is we don't have as much stuff coming out from each FFT as we did for overlap add. So we need to make sure that we do this block processing often enough so that we get all the outputs that we need. So what we need is the input blocks to overlap, because we need to kind of go back and catch things that had been thrown away because they were wrongly computed from the previous block. So same old, h of n has length nh, undetermined streaming input. Here's what we're going to do. The first thing we're going to do is pre-append n-1 zeros to our input stream. So that's easy enough to do. Just before you start filtering anything, you've got a bunch of zeros sitting there, and your first signal sample comes in and gets put there, and then the next one there, and the next one there, and we go all the way out to there. So we put in L input samples. Now I didn't take pains to keep notation similar to Peratt's, because I'm really basing this on Proakis and Manolakis' book. So, but it also helps keep straight. When you see NB, you're talking about overlap add. When you see L in these notes, we're talking about overlap save. So our first block is going to be L input samples and some pre-appended zeros. And then we take all of that and we put it down here. Then what we do is we take the next L samples, and they end up down here. But we also grab the previous NH-1, which are sitting here, and those go there. So here we pre-appended zeros. That's because those were assuming the signal to be zero before non-zero things start. Those are the previous signal samples. So it's not like we're really doing two different things. We're just doing the same thing. So every block consists of a new set of L samples and the previous NH-1 samples. And for the first block, those previous ones are zeros. So look, our input blocks are overlapped. So for overlap add, the name overlap came from the fact that the output blocks were overlapped. And for overlap save, the name overlap comes from the fact that the input blocks are overlapped. And remember, as I just said minutes ago, we're doing this because when I compute from this, I'm going to be missing, the output's going to be missing some of the stuff. And I need to go back and include these input samples so that when I do this next one, I end up with the right things. And we'll see how that works on the next slide. So if you want a mathematical definition for how we define these blocks, we just can write it this way. And this has the tilde, so that means it has the pre-appended zero. So that's just for mathematical notation. And our L here is a design choice. Notice that L is not the actual block size, right? It's the part that is the length of the new samples that are coming in. So our second block has L new samples and NH-1 old samples. So the actual block size is L plus NH minus 1. Okay, so that's our definition there. And so that's what we're calling N. Okay, so now we're going to compute the endpoint FFT of this. So remember that N was this L plus NH minus 1. So guess what? It makes sense to choose L since that's a design choice. So for a given NH, we're going to want to pick an L so that this thing is a power of 2. And generally, we will pick L to be bigger than NH minus 1, but don't have to do that, I suppose. Although I better not say. Typically, we pick L to be bigger than NH minus 1. So now, no zero padding. Our block has actual values in it over all of its positions when it goes into the FFT. That's very different from what we did for overlap add. Remember overlap add, we zero padded signal block and filter block. Here, no zero padding on the signal block. Now the next thing we do is we zero pad the H. See, we are taking L such that the N value is bigger than NH. So we zero pad it out and we take the FFT. So no zero padding for the signal blocks, but zero padding for the filter. And this can be pre-computed, right? Because we will have chosen L. We know what N is. We know how many zeros to pad and so forth. Now, when we're processing, we take this computed DFT, do the product, do the inverse DFT, and we'll call that y sub I of n, and we'll have n values coming out of that. But only some of them are good. Which ones are bad? The first NH minus 1 values are wrong. So notice this is exactly the scenario that we did if we're just looking at a single block here. We have a signal that had no zero padding, and we zero padded the filter out to the length of the signal. That was the scenario we did in that little circular convolution demonstration. And what happened? We saw that the first several values were wrong, and then we saw a bunch of values were right. So we throw those away and we keep these. And it just turns out that these blocks now can be laid down end to end with no overlap. So we save them. So the overlap here is in the input side, and we have no adding. We just save them directly to our output stream. So that's a little nicer in the sense of mechanizing this. And I think that might be why Gardner picked overlap save for his algorithm. But I really suspect, I've not worked out the details, but I think you could do it with overlap add, but it might not be as convenient to do. So here's our structure. So I took this figure from Proacus and Monolacus, but I added the stuff in red to just make it be a little clearer. So we pre-append NH minus 1 zeros. We take a block that's L plus NH minus 1 long, and we compute the FFT of that with no zero padding. Here's our H of K that's been pre-computed with zero padding. We form the product, do the inverse FFT. We get all of this stuff and we throw this away. And what happens? This edge goes into the output stream at the same position that the input started, not counting the pre-appended zeros. Then what happens? Then we take the next set of L new samples, and they come down here, and we take the previous NH minus 1 samples, go in there, compute the FFT with no zero padding, multiply by the filter DFT, do the inverse FFT, and we get this whole block, throw away the NH-1 points at the beginning, take the rest, and put it right up against the edge of the end of the previous block. No overlapping on the output, just save a block, save a block, save a block. No overlapping, contiguous saving. And that's how it works. And again, I'm just pointing out no zero padding on the signal blocks. Okay, so this is just laying out the steps in an algorithmic way. I'm going to go through it a little bit quick because it's pretty much the same as before. Choose our output block size, zero pad, pre-compute the filter FFT. Now we're going to run this for each block. Same old, same old. Compute the endpoint FFT of the input block, no zero padding, multiply by the filter's FFT, compute the inverse FFT, discard the first NH-1 elements, and save the remaining L samples of it to the output buffer, and just keep going. So that's how that works. Now, we could do the same thing and look at picking L to optimize this. I didn't go through that here. That's because it's not terribly important for our purposes, because we'll see in the next set of notes that there will be other reasons that we'll be picking block sizes driven by other things. But one could do the same, and one could account for the computational, you count the computations, and you could do a contour plot, and you'd find it would be very, very similar. Might not be exactly the same, but it's very, very similar. I've never really done that analysis to see, but I suspect that there's not a big difference between them. If there was a huge difference between them, I think you'd see that people would present one and not the other. So either one, I think, works just as well. Like I said, in Gardner's algorithm that we'll see in the next note set, he uses overlap save. I think that's largely just because it is more easily mechanized for that more complicated algorithm. Okay, so why can't we just use this? Well, there is a latency, right? We can't get any output out until one whole input block comes in. And like I said, those input blocks might be, a quarter of a second, a tenth of a second. If there's a latency in audio that's more than just a few tens of milliseconds, it disrupts. A musician can sense that, and it will throw off their ability to play in real time. So we need a really low latency. And in fact, we'll see in the next note set that we can do this with actually zero latency. And that is pretty cool. So for a block size of NB, like I just said, and now I'm kind of going back to the overlap add view because I'm using NB, but it's the same. First output sample can't be produced until after the first block has been collected and processed. So you wait for the collection, and then you also have to wait for the processing time. So a small additional amount of latency there. So just as an example, suppose our block size is 100,000. I don't know if that's reasonable, but you go back and look at that contour, but that's going to be a latency of 2.3 seconds. That's huge. But I already alluded, if we made that just 10,000, that's a quarter of a second. 1,000, that is 1/40th of a second. So what is that? It's like 0.025. That's 25 milliseconds. So we're getting close to the kind of latency that's not good. So if you're just doing filtering for non-real-time playback, this kind of latency might not be an issue. Could be, but might not be. But we're interested in implementing a reverb algorithm that someone could play through, and it would sound like they're playing in the room. That's what we're after. So for live sound, or monitoring during multi-track recording. So you're playing to a track, you want to hear what you're going to sound like with reverb. You're going to want to hear what the already recorded tracks sound like with reverb. So you need to be able to do this in real time. So the thing we've seen, overlap add, overlap save by themselves, not suitable. But as I've already alluded to, overlap save is a building block that we can extend and apply in a new way, so that not only can we use the computational complexity reduction of overlap save, but we can also remove this latency issue. And that's what we'll see in the next note set, and I hope I'll see you there.